Okay, so in the most recent video I discussed how to get the units of measure when you differentiate. So we have position, velocity, and acceleration. And now I want to talk about the units of measure when you integrate. Okay, so taking you back to the very first example of integration, we said if the velocity is 30 miles an hour for 4 hours, then, and again, t is in hours, and velocity is miles per hour. Okay, so then you'd get 4 hours times 30 miles per hour, and you'd get actually the area of this region here, and this region happens to be a rectangle because the velocity is constant. So if the velocity is constant, and you find the area, you're actually finding that area is equal to the distance traveled, and we know that that's distance when we integrate the area. When we integrate the velocity. But why is that? Well, we'll get to that. But let's talk again about units of measure. The area is length times width. The length of this is 4 hours. The width of this rectangle is 30 miles in 1 hour. 30 miles per hour. Well, look what happens with the hours. The hours cancel, and you get 4 times 30 miles. So you get 120 miles. Okay? Again, just like the last video, I'm not as concerned about the numbers as I am about the units of measure. Because the units of measure are what really, when you understand them, then you get a greater understanding of how all this stuff works. So let's take a typical rate of change function, and again, this rate of change happens to be the rate at which the position is changing. So we call it the velocity in miles per hour. And we also know that t, the horizontal axis, is represented by t in hours. Okay, so we have miles per hour and we have hours. When we integrate from a to b, the rate of change of a function, and this rate of change is, again, the velocity, the rate at which the position is changing. When we integrate that, we actually get the net area between the curve and the t-axis. Well, guess what? That's still in length times width if we use one rectangle to approximate the area. The rectangle has dimensions length times width, or base times height, however we want to call it. The length of the rectangle is in hours, and the height of the rectangle, or the width, whatever, is in miles per hour. So we're still finding area, and we're still looking at this as finding the area of one rectangle and integrating it, or adding up an infinite number of rectangle areas. And then when you multiply the hours times the miles per hour, you just get miles. So when you integrate a rate of change, and that rate of change is miles per hour, then what you get is the time, the time measurement, or the time unit cancels it out. They cancel each other out. Okay? So now let's look at a general rate of change function. Let's call this r of t, and let's say r of t is the rate of change of a quantity over per unit of time, and let's just say, for sake of having a concrete example, that we use t in hours, and r of t is represented, let's say, the number of cars that cross through an intersection per hour. Rate of change is, let's say, cars per hour. Cars per hour going through an intersection at some time. Okay, at some specific time. So from A to B, we have, let's say, noon to 3 o'clock. Okay, p.m. So for 3 hours, we could measure the rate at which the cars are crossing through or traveling through the intersection, and we could measure that in cars per hour. Okay? And if we integrate what we're really finding is the number of cars that traveled through the intersection from noon to 3. So if we integrate from noon, we'll call that times 0, to 3 times 3, the r of t, that would be hours, so length times width. So again, we go back to the rectangle. What are the dimensions of the rectangle? The dimensions of the rectangle are hours times cars per hour, and then the hours cancel out and we get the number of cars. Okay, the number of cars that have traveled through that intersection from noon to 3 o'clock. Okay, so let's take it one step further. Let's just say this guy represents r prime of t. Okay, r prime of t, and then let's say this is our A and this is our B. And r prime of t then would be cars per hour. And this is the hours. Okay, so t is in hours. R prime of t is the derivative, or the rate of change of the rate of change. So r prime of t is in, again, if we look back here, the derivative r prime would be change in y, cars per hour, as we talked about in the last video. And now we have cars per hour, and if we integrate that, and then we're finding the area there, yes. But if we use one rectangle, what is that? So the integral from a to b of r prime of t dt, that's, again, I don't care about the number, I care about the units of measure. This is hours, the length of the length is measured in hours, and then we have cars per hour. Okay, and look at one of those guys cancels. So we get cars per hour when we integrate r prime of t. Okay, cars per hour. And so we get r of b minus r of a, and that would be just the rate at which the cars are traveling through the intersection at time b minus the rate at which the cars are traveling through the intersection at time a in cars per hour. Cars per hour. So I guess this is not super critical information, other than you can just see the rate at which the cars are traveling through the intersection at the different times, and you can take the difference in the rates at which the cars are traveling through the intersection at these two different times. That's all the information. You can analyze that any way you want, but that's what it means. Cars per hour. Okay, so hopefully that clarifies a few things. Please go back and fix your responses to the discussion topic number 1, and I will see you in class.